Ooh, you guys, I'm getting a new phone today. I'm so excited.
That's exciting.
Yeah. It only took like 6 months of living with me and complaining about my phone for my partner to be like, I'll just buy you a new one. I was like, thank you. Okay. So let's just look at a couple of examples really quickly. So we said that there are two main things that you have to have in order to have a polar molecule, right? Polar molecule. So we said you have to have polar bonds, right? And you have to have some kind of a symmetry, right? So these are the things you have to have in order to have a polar molecule. So asymmetry, we said, can be a geometry with lone pairs, right? Or it can be different attached atoms.
So I guess I don't understand what that means, different attached atoms.
Let's talk about it. Okay.
Okay.
So, let's say we have carbon tetrachloride. And I'm kind of breezing by the how to draw this molecule. So I apologize if that's something that you're still kind of struggling with. We can talk about that in just a second. But I'm just going to go ahead and assume that you guys could do this structure. Now we're looking at how do we evaluate that structure, right? So I have carbon bonded to 4 chlorines, right? So are these bonds going to be polar? The bonds between carbon and chloride.
Yes, they are.
Yeah, absolutely. Does that make sense, guys?
No, I don't understand why you know they're polar just by looking at them. Is it because of carbon and whatever Cl is?
Because there's 2 different atoms? Is that what it is? Or
it's 2 different atoms, and specifically those 2 different atoms are... Sorry, I'm reaching for stuff over here. Are different electronegativities. Let me see. Guys, I have no idea where my lab manual went. Oh, good. I have it in here. Very nice. Okay, so these are the electronegativity. Sorry, it's kind of hard to see there. But you see fluorine is the most electronegative, right?
Yeah.
And going down and away from fluorine, your electronegativity decreases, right? So, it's kind of hard to see here, but if we're looking at hydrogen, right, it has an electronegativity value of 2.1, yeah. And if we're looking at carbon, we have 2.5, right? So the difference between carbon and hydrogen would be 0.4, right? This is non-polar.
That's the cutoff, right? That it has to be above 0.4.
It has to be below 0.4.
That's not on our periodic table, like the one.
No, it's not. It's not. No, okay. But it is in the lab packet. I mean, it is in the lab, and it is in your lecture packet as well.
Okay.
So this is the lecture packet that I'm looking at here, right?
Okay.
So now when we're looking at carbon and chlorine, right? We have carbon let's do chlorine first, is 3.0 and carbon is 2.5, right? So that's going to give us a difference of 0.5.
So it's polar.
So it's polar. Not
So
super.
we need that chart basically, unless
Oh. You don't. And here's why. Okay, so the numbers to me are less important than knowing that carbon and hydrogen will always be nonpolar. Okay? I don't expect you to have all of these values memorized, right? And I'm not going to give this to you on a test. So it's not about knowing who's polar, it's more about knowing who's nonpolar, okay? So carbon and hydrogen, always nonpolar, all right?
And they're bonded together, you're saying?
Correct. So literally having a carbon and hydrogen bond, this bond between them is nonpolar. Okay? And then anything bonded to itself. Right? So this will be nonpolar, and this, whoops, will always be nonpolar. Okay?
Okay.
So those are the two things that are nonpolar. So even without knowing the difference in electronegativity between these two guys, we're just going to assume that because it's not carbon bonded to hydrogen and it's not something bonded to itself, that there is a difference in in electronegativity, and so we have a polar bond here, right?
Gotcha.
Cool.
And that's why most things are polar, and that's why you say just remember what's non-polar, and
Exactly.
that's easier.
Exactly. So, and we talked about in Monday's lecture, we talked about dipoles, right? So we could draw a dipole for each one of these bonds, right? The dipole always points towards extra electrons and always has a positive charge, a little positive butt, where the electrons are not hanging out, right? Or where there's less electrons. Does that make sense? And
Yes.
we know that chloride wants electrons more than carbon, right? Because that's the trend. Does that make sense?
Yes.
So going diagonally away from fluorine, right? Everything gets less electronegative. Does that make sense, guys?
Yes.
Cool.
Professor, I have a little question.
Yes.
For example, there is this carbon monoxide,
Mm-hmm.
and that is a linear thing, right?
Yeah.
But do you want us to write the plus on the C and the minus on the O, or just the dipole arrow to indicate?
So what you actually need to do is find the formal charges, but let's talk about that one in just a second, because
Okay.
I want to finish talking about this this polarity here, right? Okay, so here we have polar bonds, right? We just went over that for sure. We know we have polar bonds, right? So we checked that first box, right? Does that make sense, guys?
Yeah.
Cool. So the next thing we want to check is, do we have asymmetry? So we said there's two ways to have asymmetry. One is we could have a geometry with lone pairs. Are there any lone pairs on this guy?
No.
Yeah.
No, right? Again, we're talking about the central atom, right? We're not
Oh, the
talking.
central atom. Okay,
Yeah,
yes.
we're not talking about all of the atoms. We're just talking about the central atom. Okay?
Okay, yeah.
So, we said no to this, right? And then different attached atoms. So, all of the atoms that are attached here are chlorines,
Oh.
right?
Okay.
So, if all of the atoms that are here are chlorines, then that means that all of these chlorines are pulling equally and opposite on the carbon, right? And so, because they're all pulling equally and opposite on that carbon, there's no net dipole, meaning there's no one area of this molecule that is hogging more electrons than another. Does that make sense? So,
Yeah.
also this is a no, right? Now, just to illustrate fully the point that I'm making, if instead of having a chlorine here, we had a hydrogen, right? Is this a polar bond?
Yes.
No, it's non-polar because
That's not polar.
Carbon and hydrogen is always
That's right.
non-polar,
Yes.
right? So now I do have different attached atoms, right? Because I have 3 chlorines here and then 1 hydrogen. Does that make sense?
Yeah.
Cool. So what we're going to have in this molecule is we know that the electrons are being pulled by the chlorines, right? So what we're going to have is a net partial negative on the bottom of this molecule. Does that make sense? So there
Yes.
are some components of the chlorides which are going to cancel out, right? Because they're all pointing in equal and opposite directions. But overall, there's still a net dipole pointing down, right? And that's because this is a nonpolar bond, so it can't cancel out the one that goes down. Does that make sense?
Yeah. So is that new molecule? It's polar.
So the last one had polar bonds, but was a non-polar molecule. This has polar bonds and is a polar molecule. Okay.
Okay.
Let's look at another example, yeah?
Yeah.
So I think this one's a little bit easier to see because it's linear. So we've got carbon dioxide, and carbon dioxide, carbon bonded to oxygen. Is that going to be a polar bond? Yes.
Yes.
Absolutely, right? So we definitely have polar bonds. Right? Check. Do we have different attached atoms?
No.
No, we do not. Are there any lone pairs on this central?
No.
No, there are not, right?
No.
So,
Okay.
if you have both of those boxes can't be checked off, right? Then what's going to happen is you're going to have your dipoles here that are pointing in equal and opposite directions, right? And so they cancel out, right? You can think of this as kind of being like a tug of war, right? Where the strength of the tuggers on either side is what we're looking at, right? If both tuggers have the same amount of strength, then there's no net movement of this carbon's electrons. Does that make sense? If we had different atoms, then we'd have different strengths of pulling on either side of the carbon, right? And the net would be that carbon's electrons would end up moving towards the stronger of the polars. Does that make sense?
Yes.
Cool. Let's look at one more. Sorry, I can do better. Okay. So this guy is ammonia, nitrogen trihydride. Do we have polar bonds?
Yes.
Yes. Yes, we do. Do we have different attached atoms?
No.
No. Do we have a geometry with lone pairs?
Yes.
Yes, we do, right? So these
Mhm.
lone pairs right here make it so that we have more electrons being pulled towards the nitrogen here than are around the hydrogens, right? So this pulling of hydrogen's electrons away from it by the nitrogen, right, is going to create a partial negative up here by nitrogen, right? Which is the definition of a polar molecule.
Oh, so if we were drawing the dipoles for that, the
Yeah.
arrows would be towards hydrogen and not towards nitrogen.
No, opposite. Right? Like these.
So I did that
Mm-hmm.
for the lab, and Professor Gregory told me I had a slight issue with that problem. So do you have to add the charge when you draw the dipole?
I'm not sure what
Sorry.
he's trying. I know. I'm trying to understand. So there's 3 dipoles here, right? One for each one of those nitrogen-hydrogen bonds.
Yeah.
Right? And so there's some amount of the dipole that is canceled out in terms of the hydrogens, right? I think this is a little bit easier to see with a smaller molecule. But let's just talk about the net dipole on this one, right? The net, not the bond dipoles, but the net dipole would be something like this, right?
Because for number 4 on lab, we almost have that same exact question. It says draw the dipole, and we're only supposed to draw one arrow.
So does it say draw the net dipole?
No, it just says draw the dipole.
Okay.
And it says draw the dipole and in the proper orientation.
So that, okay, so that's implying a net dipole.
Okay.
So net dipole is not the individual dipoles, right? It's the leftover dipole from after everything else cancels out. So let's talk about a slightly more simple molecule to look at that. And it is illustrated in the background of the lab, but I think it's just confusing enough that it's helpful to go over it. Is everybody comfortable with why this is a polar molecule? Cool.
Yes.
All right.
Professor,
Yeah.
I have a question.
Yes.
For the homework, I'm confused about PO3 3 minus. Why is it a polar molecule?
Let's talk about that in a second. But long story short, anything that has charges on it
Yeah.
is always going to be polar. In fact, it's more than polar. It's actually ionic.
Oh, yeah.
Okay?
Thank you.
Yeah. So we generally talk about polarity in terms of non-charged molecules, right? Because if you have a charge, then we move past polar and into ionic behavior, right? Okay, so this guy is water, right? Everybody's okay with the fact that hydrogen and oxygen have different electronegativities, right? These are definitely polar bonds.
Mm-hmm.
Okay. And we also have lone pairs, on the oxygen, right? So we have asymmetry, so this is definitely a polar molecule. So when we draw the dipoles, right, where are the arrows going to be pointing here?
Towards oxygen.
Right. Everybody okay with me on that?
Yes.
So technically speaking, if I was a better drawer, these arrows would be equally sized, right? Because the size of the dipole tells you about the strength of the dipole, okay? So now what we want to look at is how we break down the components of these dipoles, right? How certain parts of them will cancel out and certain parts of them will add together, okay? So this is looking at each one of the components of the dipole separately. So I'm going to redraw this really quickly. So it's a little bit bigger so that I can actually use it. So this dipole here is going to have a component that points in the XY direction, right? And another component that points in the Y direction, right? Or, I'm sorry, this is the X direction, this is the Y direction, right? This dipole over here has a component that's pointing along the X direction and another component that's pointing in the Y direction, right? Now again, we're pretending like these are good drawings and like all of the arrows are equal, right? That they're the same size. So when we add these two guys together, right, they cancel out. So again, if my drawings were better, what we would see is that we have two equal and opposite polars here, right, in our tug of war. So they cancel out, okay? But we have these two components, right, that don't go in opposite directions. So these guys add together. To make one big dipole, right? And so what that means is when we draw the net dipole, right, we draw this guy.
Gotcha.
Does that make sense, guys?
Yeah.
Cool. This is confusing. So, and it's also really hard to see this, right? So that's why when I talk about symmetry, I kind of oversimplify and say that if you have lone pairs, right, then you will have asymmetry, right? And that asymmetry means that you end up having a net dipole. Does that make sense? If you don't have lone pairs, then what happens is all of these weird little components of the dipoles are going to end up canceling each other out, right? When you have no lone pairs and the same attached atoms, all of these little dipole components will cancel each other out.
So a polar molecule with no lone pairs will not have a net dipole?
A molecule with polar bonds that doesn't have lone pairs or different attached atoms will be a nonpolar molecule. Even though it has polar bonds, it will still be a nonpolar molecule.
So what if it's what if it has polar bonds and different attached pairs but no lone pairs?
You mean different attached atoms?
Yes. Sorry.
Yes. No, that's fine. So that was like the example that we gave with the carbon tetrachloride, where we replaced the hydrogen, or we replaced one of the chlorines with a hydrogen, right?
Okay, yeah.
So that would be an example of when, again, we broke that symmetry, and the symmetry is what allows all this cancellation to happen.
Okay.
Right? What's up, Rachel? I'm sorry, Rochelle. I know this.
Okay, good morning. Okay, so I'm sorry if you hear my dogs in the background, but for the homework, I just can't remember for letter F. It's carbon, it's the CO. I know how to get to the actual drawing of it, but that also follow the octet rule. In the homework, it's number 1, it's letter F.
So I think this was the one that you were having a question about also, Juan Carlos. So let's look at it. I'm going to go ahead and take a quick break from recording.